Hello, Lower Six. We have one more lesson to go on materials, and then we've finished the mechanics part of the Lower Six syllabus. In fact, we're right on target to where we should be at the moment in the Lower Six syllabus. We would have finished this before you went on study leave for the internal exam. This would have been the last thing you would have been examined on at the end of May. So we are on target, and after this lesson, you will get a end of topic test to do, hopefully electronically, by the end of the week. Just to push on, then the end of the final part of the mechanics topic is going to be looking at Young's modulus and stress-strain curves. So if you remember in the last lesson, we defined stress and strain as alternative ways of measuring the properties of a material when it's being stretched, instead of using force and extension. The advantage of using stress and strain is that it takes away the dependence of the material on its length and its cross-sectional area, and allows you to just look at the properties of the material itself when it's being stretched. So what you're going to have to be able to do is interpret a stress-strain curve, and also you will have to measure Young's modulus or use Young's modulus in a calculation. So to help me explain how you would do this, I've got a graph that's drawn here where I've got two stress-strain curves, one for glass and one for steel. So I'll just stand up and show this to the camera. Okay, so this is what a stress-strain curve looks like for these two materials. So on the y-axis there, we've got the strain in megapascals. Now remember, the strain is the force per unit cross-section area as we're stretching the material. And then on the x-axis, we've got the strain. So the strain is the proportional increase in the length of the material. If we were able to go to a strain of 1, that would be doubling the length of the material. It's very unusual. You can get that high a strain. So that's a stress-strain graph. And the first thing that I'm going to point out to you on this graph is the first part of the graph. So we've got glass here and we've got steel. What you'll notice is that for both of these materials and for many other materials as well, the first part of the graph is a straight line. In other words, stress and strain are directly proportional to each other. So in other words, it's very similar to Hooke's law when we're plotting force against extension and we got a straight line. You will notice that the gradient's different. So on this graph, the glass has got a steeper gradient than the steel. And that gradient is obviously the constant of proportionality between stress and strain, which we call the Young's modulus. So if you wanted to work out the Young's modulus for steel, all you would do is you take the straight part of that graph and you'd work out the gradient of that graph. Or if you were given a value for the stress and the strain, you would just do stress divided by strain, as long as you're on that straight part of the graph. Okay, so that's the Young's modulus. The unit of Young's modulus is the same as the unit of stress. It's in pascals, although actually for most materials it's a very high number of pascals. So for instance, for steel, I can't remember the exact number, but it's something times 10 to the 11 pascals. You can think of the Young's modulus as being the stress required to double the length of a material, to give it a strain of 1. Now that in reality is impossible for most materials, because they would break before you got to a strain of 1. But if you imagine this straight line part of the graph, if that kept on going forever until you reached a strain of 1 on the x-axis, then if you measured the strain at that point, the stress at that point, the stress would be the same as the Young's modulus. Okay, so that's what we mean by the Young's modulus. Another way of comparing glass and steel here is to say that the glass is stiffer than the steel because it doesn't strain as much for the same stress as the steel does. Okay, so that's the first part of the graph. And then on to the rest of the graph, which does look a little bit more complicated than your normal force extension graph. So we're going to look at the steel first of all, and similar to force extension, you have a limit of proportionality, which I've labelled as P. So beyond that point, you can't use the Young's modulus to relate the stress and the strain. You also have, I've labelled E, an elastic limit, which is the point beyond which the steel would be permanently deformed. So again, that's similar to the force extension curve. You'll then notice that we do have these two strange points here, Y1 and Y2. Now these are called yield points, and that's because steel does something a little bit strange. When you stretch it beyond a certain point, the molecules in the steel reconfigure themselves, they sort of realign. And at that point there's a sudden releasing of the tension in the steel as the steel stretches. So that's why as you're stretching the steel in this direction, the tension will drop slightly between Y1 and Y2. It's because the molecules in the steel are realigning themselves. Once you get past Y2, as you increase the stretching of the steel, again the tension will build up. So as you can see, the stress is going up and the strain is going up. You get to this point which I've marked UTS, which is the point at which you have the maximum tension that you can possibly have. The UTS stands for ultimate tensile strength. So, there's a couple of numbers you can read in a reference book for steel. You could read the Young's modulus, and you can also read the ultimate tensile strength. Now, the ultimate tensile strength is the maximum. If you read off the y-axis here, it's the maximum tension, the maximum stress that the steel can withstand. So the stress being, of course, tension per square meter. Okay, then beyond that, if you try to stretch it beyond that point, eventually it just breaks. Okay, and the steel would snap. So that's the curve for steel. Now you would notice that the curve for glass is a bit different. You've got the Hooke's law, sorry, not the Hooke's law, but the proportional part, and then it does curve. But you can see the glass, it only curves a very short distance before the glass breaks. That's because glass is what's called a brittle material, whereas steel, and most metals in fact, is a ductile material. The word ductile means basically you can draw the material into a thin wire. So you can pull a metal really, really thin and stretch it quite a long way. And that's why you have this quite long sort of tail from here to here, where you can, beyond the point of proportionality, you can carry on stretching the steel, whereas the glass breaks very quickly once you reach the point of proportionality. So glass is a brittle material, whereas steel and most metals are ductile. So if you come across those terms, brittle and ductile, that's what they mean. You would compare how big the curved part of the graph is to how big the straight part of the graph is. And for glass, and there's a very short curved part of the graph, so it's a brittle material. So that's almost it for stress-strain curves. So you do need to learn to be able to describe what a stress-strain curve is. You might be given calculations to do using the Young's modulus as well, and there'll be some of them in your homework sheet. Another thing just to mention as well, because it does sometimes come up, is the area underneath a stress-strain curve. If you remember when we did the force extension graph, the area underneath a force extension graph was just the elastic potential energy stored at that point. Well, it's kind of similar here. The only difference is that the area under the graph up to a certain point would be the energy stored per unit volume. So the unit of that would be joules per cubic meter. So it's the area under the graph is the energy stored, or the elastic potential energy stored per unit volume of the material up to that point. So that's basically it. I'm going to give you some notes to copy into your notebook on this. But that's a stress strain curve, and hopefully I've also explained to you the Young's modulus. This is of course related to the work we've done before on Hooke's law and spring constants and so on. It's just generalizing it a bit for all materials, and also taking away the dependence on the length and the cross-sectional area of the material. The only other one more thing that we do need to talk about is actually practically how do we measure stress and a stress strain curve. Now the problem with doing that for instance a steel wire is that steel wires, you have to put a huge force on them to begin with to get them to stretch. And when they do stretch, they only stretch by a very tiny amount. It's not like stretching a spring, which you can measure with a ruler. With a steel wire, or most metal wires, the size of the extension is it's usually less than a millimeter, even if you've got, say, a meter or two original length of steel wire. So it's not as easy as the Hooke's law experiment. And there's one piece of apparatus that, if you'd been in the lab, we would have showed you, which is Searle's law apparatus. Now, what I think I'll do is I'll do a little video. I've got the Searle's law apparatus here. I'll do a little video. It'll be a separate video from this, just showing you how Searle's law apparatus works, because it is something that you do have to learn. There is also a required practical that you have to do on this, which obviously we won't be able to do until you get back into school, where you will find the Young's modulus of a nylon fishing wire. Basically you'll have it stretched out on the table, and you'll be able to measure it. Now you don't need Searle's apparatus to do that, because it does stretch quite a bit, appreciably, that you can measure it with a ruler. You wouldn't need a Searle's law apparatus, which basically measures a fraction of a millimeter. Okay, that's it. That's the work for this week. So learning what the Young's modulus is and stress strain curves for materials. So there'll be a worksheet and obviously these videos. And the other thing to do, of course, is to revise for the end of topic test, which will be the next section. Okay, that's it. Thank you. Low 6.